break that down. Who can tell me what modulus is? Anybody ever heard of modulus? Modulus. Who can I pick on? Brewer, you know what modulus is? Brooks. Floyd, you know?
Things put together.
Kinda. I'm looking for something else though. Kinda something else. Not bad. Sean? Kevin, Parker, Jackson, Stevie? Anybody? Modulus? You might know it from math or science. Modulus it simply means a value. If you Google it, what's a modulus? It's a value, right? So it's a number. So I'm looking for a number. And I'm looking for a number of elasticity. What's elasticity?
Like how stretchy or bendy.
Stretchy or bendy, right. So when I say modulus of elasticity, don't think of the ratio of the increment of some specified form of stress to the increment of some specified strength. Think of a value for bendiness. Okay? So every material out there, steel, aluminum, marshmallows, whatever, they all have a modulus of elasticity. Someone sat down and figured it all out. They put it all in a giant chart. Somewhere there's a value. We look it up. So if I want to know the modulus of elasticity for styrofoam, I go look it up. It'll tell me what that is, right? And I put that in my formula. Anyway, so think of modulus of elasticity, a value of bendiness. Okay? Also, just like the moment of inertia, the higher that value is, if I have a high value, that's good. It's more resistant to bending. If I have a low value, it's more bendy, okay? Low value, bendy, higher value, good. All right, let's continue on. This is where I am going to, let's see here. This is where we're going to go back. We're going to put the slideshow aside for a moment. And I'm going to bring back our folks in the back there. All right. Folks at home, you're not seeing the slideshow anymore, right? You're seeing me?
Yes.
Thank you for the verbal confirmation, Trevor Mullins. Appreciate it. Okay. See if I can get those guys to see too. All right, everybody. So I don't blind myself, because every time I look at that, it hurts my eyes. Let's do that. I have two pieces of building material here. They look pretty similar, right? Same width. This is 5.5 inches wide. Same thickness, 3/4 of an inch. Same length, 59.5 inches long. 59 3/8, somewhere around in there. Who gives an 8, right? Tough crowd. Anybody out there laughing? That was a good one. Okay. They're high school students. That didn't make that wasn't funny. Let's keep going. Keep moving. Keep going. They're basically the same cross section too, right? So if I look at this, remember we talked about cross section. Now this one has a few little ridges in it. You see, those are kind of negligible, right? Just go along with me. Cross section's the same, right? So if we're talking about moment of inertia, these are pretty much the same, right? So if the moment of inertia is the same, do they have the same resistance to bending?
No, it's the material.
Ah, Floyd is on it today. Floyd, you're killing it. You're like nailing it. Okay. Material is the other component. Okay. So shape, orientation, all that's important, but also the material. That's why we're talking about modulus of elasticity. Okay. It's the material. Now, does anybody know anything about these two boards? Can they tell me about what are the differences here? What do I got? Let's start off with this first. Sorry, I'll come back to you, Matt. What are these used for? Anybody recognize this piece, two pieces of something? Seen them before?
The one on our left is what we're talking about, guessing the composite that was.
This one?
Yes.
Yeah. Yeah, composite. That's good. He said a key word, composite. He said it's for decks, right? Porch or a deck. This is the floor. So if I'm building a deck or a porch at my house or around the swimming pool or off the back patio, this would be the floor. I'd lay this down, I'd screw it down and nail it down, and this is the part I walk on, right? This is the same thing. This is a actual wood board, real board, comes from a tree. So you can see the grain and you can see the knots. If I cut down a tree and I run it through the sawmill and then I run it through the planer, I can take a tree, big round tree, and I can make it into boards. That's what I did here. Now, the problem with boards are, because they were living, they're not very, let's say, homogeneous, right? There's a lot of variation. All of this grain is doing funny things. It's twisting. There are knots in here. I cut this tree down, I slice it into a board. It looks pretty good, and then the wood starts to dry, and then it twists, and it bows, and it cuts, right? So this one is a pretty good building material, pretty strong, but it doesn't have really good properties as far as straightness or consistency. You guys ever go to Lowe's or Home Depot and you go to grab 2x4s? You kind of like see people picking them up and looking at them, and they put that one back and get another one, and then there's a big messy pile of boards, right? You can have that. This one, on the other hand, Mr. Brewer said correctly, it said Trex, right? Trex is a brand name. It's a brand name for composite boards. So if I look at this one, it's not a board at all. It's not a wood. It's made up of junk put together. Okay, not junk, but it's made up of different stuff. All right, so there's plastic in here, sawdust, rosin, glue, binders. For you people at home, I'm talking about this right here. This is a Trex board, a composite board, right? So this one has some advantages though. Comes in pretty colors. It's nice and straight. This one's all warped up. This one's nice and straight, and it's always the consistent thickness. So I don't have the little variations in the board width. But it's a different material. So modulus of elasticity is different. Strength might be different. Let's do a little test. Engineers don't always like to be like, oh, okay, I believe you. You should be a little skeptical. You should say, show me, Heartline. I don't believe you. So we'll set up our little test as we did yesterday, our little bending test. Okay. This might be a good time to put you guys back on. See? All right, let's go back to our technology here. Put this back up here. Bear with me for a second, everybody. Hang on. I'll do this as quickly as I can. I'm going to minimize this. And then if I click on this and close it, and then come back to this. There we go. They're back. All right, let's put them down here on the floor. Okay, so there's our little test fixture. All right, here, remember, same width, same thickness, same length, basically the same moment of inertia, right? All the calculations there say they're the same. However, the material is different. So let's start with this one. Wait a minute. Anybody vote? Who thinks, which one's the stiffer one? Let's see first the vote of hands for this one. The engineered wood. No? How about the regular old plain old tree wood? Okay, a few votes for that. A few people not sure. That's all right. We'll test it. Let's try this one first. Okay, we're going to put this on here. Remember, I'm going to throw a vocabulary word at you here. Anybody remember the distance from the support to support here? So remember I told you the board's 59.5 inches long, but I'm supporting it here and here. What's that distance between the supports? Span. Good. Span. All right, span. So I've got that board on there, and I got my handy dandy board. And I'm going to measure Measure right here. Got about 3.5 inches. Okay, I'm going to add 120 pounds. This kid. Let's just say 195. 195. Let's lean down here. And I'm now at about 2 3/4. So I went from 3.5 to 2 3/4, so about 3/4 of an inch. 3/4 of an inch of deflection. So let's look at that again. On. Not bad. Off. On. See, look, you can see it. 3/4 of an inch, not bad. All right. Let's try the other one. Take this one away. Put in the fancy composite board that comes in different colors. You guys ever walk on this stuff in the summer? Hot, right? So there's another thing. That's a disadvantage. It's hot on your feet. All right, let's look at this one. It should be about the same, somewhere around 3 inches. Yep, right at 3 inches. Okay, 3 inches. You ready to measure this? It's on the ground, ladies and gentlemen. It is bent all the way down. If I would raise it up, it'd probably bend even more. It'd probably even break it. You know what though? I was saving that for you guys because I didn't want to do it earlier in the day because then it'd be broken and then you guys wouldn't get to see it. But you guys want to see how much it'll really bend? Okay, let's raise it up. All right. So just in case. Is there still a phone right over there? Real close? Okay. Do you know the number for 911? Okay. Just in case I fall. Just in case I fall. So that was quite a bit of deflection, right? Quite a bit of deflection and then failure. All right. So what's the lesson there? What did we learn? We learned that Heartline stands on boards and breaks them. What did we learn? The anxiety beam is back. What did we learn? It doesn't just matter about cross section. It doesn't just matter about orientation. Michael Smith, what else matters? Orientation, cross-section, and modulus elasticity, right? The material. Yes, if you said material, we're talking about modulus. Remember, modulus is a value. Modulus of elasticity, value of bendiness. Okay. Value of bendiness. How are we doing on time? A couple minutes left. Good. Perfect. Perfect. Any questions on any of that? Any questions on any of that? Vetter, any questions on any of that?
No.
It seems like you're distracted. Are you able to, are you with me? Okay. All right. Just checking. All right. I just worry about you, Vetter.
I just act distracted.
You act distracted. That's a good one. All right, here we go, guys. I got a little short 3-minute video for you. This guy, I really like this. I'll tell you why in a minute. Let me make sure that we can share. Now, so for your folks at home, I'm going to share this with the people in the classroom here. I don't think you'll be able to see it at the same time when we're watching it because it doesn't allow you to do that. But the good news is I didn't forget you. I put the same exact video in your Canvas page. So if you guys want to go over to the Canvas page right now and click on the link, on the YouTube link, you'll watch the same video that we're going to watch right now. Okay? Go ahead. And then let's do this, share, click on this, and click on this. All right. So what I think is pretty cool about this video is it's just 3 minutes long. It's a guy who's he's one of these science guys, right? But anyway, he says, I want to make something strong out of something weak. Right? So we know modulus elasticity we know the material is important on how strong something is. He said, what if I take a weak material and make it strong? How would he do that? What did you learn in the last 2 days that could help you make something weak into something strong?
Make it as big as possible.
Big as possible. What else? Reinforce it. Shape. Who said shape? Better you were paying attention.
Exactly.
I apologize. See, I looked over there and you're looking down. I thought maybe you were distracted, but you were on it. See? Good job. Good recovery. Way to clutch up. Better. All right. Anyway, so he wanted to take something weak. Sorry. He wanted to take something weak and make something strong. Is styrofoam weak?
Yes.
This guy in the video, he's going to take something weak, make out something strong. Right? This is pretty weak. Styrofoam breaks pretty easy. You think I could make a beam out of this and stand on it? No?
Or maybe.
You're skeptical now. All right. Watch and see. 3 minutes. You can do this. Did that right? All right. Here. Doing it. Oh, okay. Double or nothing. So what do you think? He took styrofoam and some bendy plywood, and by creating a shape that we recognize, that I-beam, he's able to hold up 400 pounds with some foam in there. Again, shape, orientation, and material. All those three things work together.